Hi everybody, Jonathan here. In this video I will be giving you my take on section 8.2, which is about the area of a surface of revolution. So everything in this section is very similar to what happened in section 6.2 and 6.3, where we calculated the volumes of revolution. In that we took an area and we rotated it around some axis and then we got a solid. Now, instead of taking an area, we're just taking a curve. If you just rotate the curve, then you are going to get a surface. It's like the solids you get in section 6.2 and 6.3. We'll just be calculating the surface area of those solids in this section. So, in order to make a nice approximation of the surface area of a solid, we first have to know what the area of a frustum is. A frustum is simply a truncated cone. So there's a lovely picture of a frustum here. It's a truncated cone. And the book very carefully derives a formula, which unfortunately isn't until the next page. But in their formula, what you do is that the area is going to turn out to be 2 pi times the average of these two radii, the radius of the two circles, the average of the two radius of the two radii that form the frustum, and as well as the length of the side of the frustum. So the length, you got to be a bit careful here. It's not the height, it's just the length of the side. And here's the formula they came up with for that. A equals 2 pi RL. Again, R is the average radius of the two circles that form the frustum, and L is the side, sort of like the diagonal side of the frustum. Now, I made a GeoGebra app in order to show how we can get the surface area of one of these surfaces of revolution. So first we can create the surface. So here we're going to take the curve y equals sine x plus 1, and we're going to rotate it about the x-axis. And as we rotate it, in this case, you get this lovely kind of fish shape. So how can we calculate that thing's area? Well, the way we're going to calculate it is we're going to approximate it with frustums. So if you take a line segment, let's see if I can show you. Here we have this line segment, and if we rotate that line segment about the x-axis, we get a frustum. Technically, we're not getting the top and bottom of it, we're just getting the sides of a frustum. But it's that area that we need to know. And again, the formula the book kindly derived for us was that the area is 2 pi RL. Now here, R is the average of the radii of the two circles on either side of the frustum, and L is this diagonal length here. It's the length of the side of the frustum. Now, what we're going to do is we are going to approximate the curve with these straight line segments. Right now I've got n equals 3, but I can increase that and get more and more line segments to get a better approximation of the curve. Each of those line segments, when we rotate that about the x-axis, is going to form a frustum, and then the union of all those frustums is going to approximate the solid. So right now, if I rotate, then we get, in this case, n is 3, and we get 3 different frustums, 1, 2, 3. And if I go ahead and show the solid on top and then hide the frustums, it's not great, but you can see that the shape of the frustums is approximately the shape of the surface we are trying to approximate with frustums. And furthermore, if I go ahead and increase the number of frustums, so maybe make it 7 here, then we'll get a better approximation. So there is the surface. Here is all the frustums, and it's still not perfect, but it's getting better, and I'll increase it more and more. And then that's the right most I can increase it here is 10, but at that point already you can see that we're very close to having the frustum surface be the same as the actual surface we care about. So to approximate the overall area, we're going to calculate the area of each frustum. So we take the frustum over the ith subinterval. Now on one side, its radius is just going to be the distance up to the curve. Let's see if I can show this. So the radius is just going to be this distance up to the curve, which is therefore the f of xi. And then the radius of the other circle is going to be this distance up to the curve at the right endpoint, and that's going to be f of xi plus 1, and then we have to average those two. So we're going to get the area of just this middle frustum, when I go ahead and rotate it, to be 2 pi times f of xi plus 1 plus f of xi over 2, because we, again, are averaging the two radii. And then we have to calculate this length. This side here is, this point here on the curve is the point xi comma f of xi, and this point here is the point xi plus 1 comma f of xi plus 1. And we use the distance formula on that. Since the distance between xi and xi plus 1, the difference between the x values is delta x. So this length is going to be the square root of delta x squared plus the f of xi plus 1 minus f of xi quantity squared, because this difference in these f of xi's is the difference in the y values. And doing the exact same trick we did for arc length, if we factor a delta x squared out inside the square root and then factor outside of the square root, it becomes a delta x, and it leaves behind a 1, and it leaves behind this quantity of f of xi plus 1 minus f of xi over delta x, all that squared. Now this next part is going to look slightly funky, but again we use the mean value theorem, and we're able to write this as f prime of xi star for some point xi star in that ith subinterval. And furthermore, once we have the number of subintervals really large, then their width becomes very small, so this f of xi plus 1 is going to be about f of xi is going to be about f of xi star. And therefore, we're approximately just adding f of xi star itself and dividing by 2, so you just get f of xi star in the end. Now these can all be added up, and you can take the limit as n goes to infinity, and we get this amazing formula that the surface area is going to be the integral from a to b of f of x times the square root of 1 plus f prime of x squared dx. For some very good reasons that you might not see until you're in Calc 3, they like to express this formula for the surface area in terms of Leibniz notation. So in terms of Leibniz notation, the surface area is going to be the integral from a to b of 2 pi y, because y is the f of x, times the square root of 1 plus dy dx quantity squared dx. Now, if for some reason you want to rotate if for some reason you have everything, if you have x as a function of y, the exact same formula still holds, because this expression here, the square root of 1 plus dy dx quantity squared dx, actually equals the square root of 1 plus dx dy quantity squared dy. So this same formula will hold if we solve x, if we have x as a function of y. Here y is a function of x, here x is a function of y. But the key thing to notice is they both have a y in this position, which means there'll be very different formulas for calculating the same surface area. Yes, one will be in terms of y, but this y here might be some complicated function of x, whereas this y here is just the variable with which you're integrating. So this is two completely different formulas for finding the exact same surface area, and that can be very useful. And in fact, all of this can be neatly summarized if we let ds be the square root of 1 plus dy dx squared times dx, which equals the square root of 1 plus dx dy squared dy. It doesn't really matter. Then the formula for rotating about the x-axis is that it's the integral of 2 pi y ds, and the formula for rotating about the y-axis is it's the integral of 2 pi x ds. However, this y or x in the beginning, you can always, assuming you can solve for x and for y as you please, you can always make this y or this x be the variable with which you are integrating, or you can have this y or this x be a function, the function for which you're finding the length. And you get two different integrals based on those choices, which can make it, it gives you sort of twice the chances to be able to find a difficult surface area problem. Now the book is kind enough to illustrate this with an example. If you look at example 2 in the book, they want to take this piece of parabola from x equals 1 to 2, and they want to rotate it about the y-axis. So first off, to rotate it about the y-axis, the formula is the surface area is the integral of 2 pi x ds, and then you just calculate dy dx, and you wind up with 2 pi times the integral of x times the square root of 1 plus 4x squared dx, which is, in this case, is quite nice. You can do a simple substitution, and you'll get that answer quite quickly. On the other hand, you can actually solve this for x, solve y equals x squared for x, and you get x equals the square root of y, and dx dy is now 1 over 2 times the square root of y. And now the integral of 2 pi x ds becomes 2 pi times the integral of the square root of y times the square root of 1 plus 1 over 4y. And again, you're integrating with respect to y. It's a dy, but it's a completely different integral. All right, the way you're going to solve this one is completely different the techniques you're going to do to solve this integral, and they both represent the exact same surface area. So again, the fact that you have two formulas for most of these surface area problems kind of gives you twice the chance of being able to find something you can actually find the integral of. Unfortunately, these formulas are going to wind up with pretty difficult integrals because you've got a square root in them. So having two ways to try and solve each one can be quite nice. Well, that's all I wanted to say. See you all next time.